All right, good afternoon, everyone. Thank you for coming to my talk on how we scale telemetry systems. Hopefully this will have some relevance to you, even if you don't work on telemetry systems themselves, because more broadly speaking, I think telemetry is a big data problem. Now, I did lie slightly in the title for this talk because I don't actually profess to offer best practices. I profess to offer the lessons that we have learned through trial and failure and more failure and more failure. There is no such thing as a universal best practice. There are only things that are from the blood, sweat, and tears of site reliability engineers and systems architects. So, as I was saying, telemetry data is basically data that we collect about our systems that enables us to make sense of what's going on in production. And the volume of them is just rising and rising and rising and rising and rising, right? Like we're writing even more log data than before. We're starting to send trace data. And more people are adopting the OpenTelemetry cloud native standard. So OpenTelemetry has gone from 2 years ago. We were in a position of being the third largest cloud native computing foundation project. We are now the second largest cloud native computing foundation project and the third largest in the entire Linux Foundation. And that's basically what the activity levels look like because there are a lot of people that are using OpenTelemetry in anger to send large amounts of data to their favorite observability provider. So that's basically the backstory. I'm not telling you this because I want to sell you on Honeycomb. I'm just here to tell you some really cool technical stuff. But I want you to be aware of kind of, why are we going to the war with the emus, right? Like the reason that we're going to war with the emus, if you didn't catch that talk this morning, you should watch the replay, it's hilarious. The reason we're going to war with the emus is because our customers care about reliably getting data about their systems, and that's why we need to ingest millions of data points per second. So 5 years ago, we were a small company of about 30 or 40 staff. We've grown not by a factor of 20, but we've grown as a company by a factor of 5. But our traffic has increased by a factor of 20. And that means that we've had to make some technical trade-offs around how do we make our system scale sublinearly in terms of headcount and server resources compared to the amount of incoming data. So 5 years ago, we were serving about 200,000 trace spans per second that were being ingested into our platform, and now we're peaking at over 4 million trace spans per second. And the number of queries people are running against that data, which is 20 times as much data, people are also querying 20 times as often, which you can squint and say that's, about a 100x increase in the total amount of data that we're scanning. And architecturally, our system is really, really, really heavily reliant on two key things. We are really reliant on streaming data systems in the form of Kafka, and we are really reliant on distributed MapReduce technology by using Serverless and by using object storage in a service like S3. So I am, by title, the field CTO. I am also still a practicing member of our platform engineering team. I still jump in every now and then to help with incidents. I still carry a pager, because I believe it's really important to be grounded in the truth of what our systems do rather than just being, someone who's off talking about architecture who hasn't touched a real system in 20 years. So today we're going to talk about kind of two halves of this, right? Like the ingest side of when it's appropriate to use streaming systems or when you could make do with something less complicated. And then we're going to talk about the storage and query side of how you actually query that huge amount of data that can come in and what some strategies are to deal with keeping it responsive and fast. So as I was saying, your use case is not exactly ours. That's okay. I do not expect you to go home and decide, I'm going to implement an OpenTelemetry pipeline today, right? I think the important thing for you to take away is to say, my problem looks maybe a little bit like a Kafka or data streaming problem, or my problem looks a little bit like a distributed MapReduce problem. Here are some of the things I might want to consider if I'm engineering my system around this. So let's talk about the ingest side first, because that's where the data comes from. So Kafka is the beating heart of Honeycomb ingest because we started Honeycomb about 8 years ago, and Kafka was kind of the standard way to deal with streaming data. There are a myriad of newer solutions since then. There's Apache Pulsar, there's Red Panda, but for us, Kafka is kind of our bread and butter that influences our system's reliability, because if Kafka is not available, then our system is not available at all. So why did we decide to embrace this kind of very complicated stateful storage layer? Why did we not decide to outsource it to someone else? Why did we not just run a straight, just run things directly through a set of workers and not even have a streaming data pipeline? So the fundamental reason why we care about streaming data is that it enables us to decouple our systems. I think there was a talk this morning that talked about the idea that you cannot really eliminate complexity, you can only move it around. And for us, what we do is we move all of the hard problems, all of the state, all of the persistence, all of the distributed systems, all this distributed systems ideas of consistency and election leaders, all of that gets foisted off onto Kafka, which is battle tested by thousands of companies all around the world, so we are not alone in case something goes wrong. Because you can imagine that if we were writing our own Raft protocol, if we were writing our own stuff here, we'd have this horrible mess where we wouldn't be able to tell, is a data consistency problem something that we did or something or something else going on, right? Whereas here, by saying, we're going to use this off-the-shelf software, this enables us to really have this idea of the stuff that we do ourselves can be entirely stateless, and then the stateful workload can live inside of Kafka. So this enables us to deploy to production a dozen times a day because we don't have to worry about kind of doing a complicated dance of, waiting for everything to cleanly start up, waiting for everything to cleanly shut down. We can just process whatever is in flight and hand it off to Kafka. And the instant Kafka has our data, right, that's persisted from our point of view, we don't have to care about it anymore. On the flip side, when we're reading the data back out, if something, heaven forbid, goes wrong, we can go back in time and we can replay from a known good point, which again gives us that flexibility to update our systems on demand rather than having this situation of, did I perfectly exactly line up the version updates of the producers and the consumers? By adding that extra layer, that means that we don't have to worry about tight coupling of that, and we can be a lot more relaxed about it. So by having all the state live in one place, right, like rolling restarts are really great. The replay in case something goes wrong is great. But the scary part is it's not our own software now. Sure, it's supported by many other people, but it is fundamentally not our own software. And also, it is software that, if it goes down, our producers have nowhere to write to, right? Which can be a little bit of a problem. So the other really interesting thing about our use case is that we are not using this in the conventional mechanism where a lot of people say, you should use event-driven architecture, right? Like you should publish all of your events related to your e-commerce site into a bus, and then, you can consume from the bus and use it to power BI systems. That's not what we're using it for, right? Like what we fundamentally need from our system is just the ordering of what happened and when, so that we have a distributed log that we can reconstruct and we can use in order to ingest all of this data. So this means that we don't have hundreds of topics, we just have one or two main topics. We also want to carefully control the allocation of partitions to workers, because we very much care that if something was written to one partition, that only the workers associated with that partition read it, and it's not like something where I don't care, you can scatter it randomly, it doesn't matter which worker picks it up. We do actually care which worker picks it up. We're also not using the Kafka native primitives like KSQL to interact with the data because we've written our own data store that ends up reading off of the Kafka queue. So what do we actually use it for? Well, the answer is we are using it as our disaster recovery solution, right? Like in the event that we have to restart one of our consumers, we go back in time and we replay from a snapshot, and then we play everything back forwards. So this is what this looks like in practice, right? Like so a customer sends us some telemetry data, which is basically a sequence of log lines or structured logs or events, we call them. And we'll go ahead and spread them out, and we'll say, I'm going to take all of the trace spans associated with one trace, and I'm going to choose to write each trace to a single partition inside of Kafka. And that way I have that data locality property and can make sure that, if I'm querying all the data associated with the trace, that I can retrieve the data for multiple spans in the trace rather than spraying it round robin. But fundamentally, every single event that's inside of a batch of events that's originally sent to us gets distributed across according to its trace ID across many different partitions inside of Kafka. And then we have indexing workers that will go and pick up the end of the feed, and they'll go ahead and decompose it into the constituent parts. And every hour or so, we will checkpoint that worker and write its state off to S3. And then in the event that we lose an indexing worker, what can happen is we'll just find the backup from an hour ago or 2 hours ago, and then we'll go look up that offset inside of Kafka and play it forward, and then have it start serving once it actually reaches the current index. So what happens if this system is not behaving according to specification, right? Like, software architects love to talk about the happy path. I'm a systems engineer by background. I love to talk about the things that go a little bit sideways. So what happens when you try to write into Kafka too fast? What fundamentally winds up happening is Kafka is trying to provide you with an ordered sequence, ordered per partition. So if one partition gets bogged down, it's not going to be able to hand out acknowledgments saying, I got your event or batch of events. So that means that we need to be able to, on the fly, choose to abandon writes that are in progress and to say, you know what? It's more important that we get this data persisted somewhere, even if it's not necessarily the partition that trace's data is supposed to go to. That way we can get it out of our hands and not be holding on to it. Why not just buffer it indefinitely? The reason is, we use actual hardware at the end of the day. You can request 16 gigabyte VMs from Azure, you can request 32 gigabytes, but at some point, you run out of memory to buffer. So either you are saving it somewhere, or you're going to and you're going to drop the data anyways. Now, our customers can and do retry, but we really, really, really prefer not to make them do that, so we actually have a service level objective that says we want to have 99.99% of persistence requests to succeed. But there are some ways, short of actually diverting the traffic elsewhere or dropping it. Namely, sometimes the problem is between one specific producer and one specific Kafka broker. And you can give it time to recover by saying, you know what? My validation worker that's handling these events coming in from the outside internet, if I get backed up and I have more than 50 requests outstanding or 100 requests outstanding, stop sending me traffic. I'm going to wave the white flag and be like, hey, I have too many outstanding requests. I'm going to push back on the traffic. There may be other workers who can service those requests. And that enables us to avoid having this situation of becoming under pressure and running out of memory. What about if there are issues with the throughput of the actual Kafka broker itself, right? So this is not, we're trying to push too fast through any one producer. This is the actual machines through which 100% of the data flows. What we find to be very helpful here is to maximize three things, essentially. We want to really, really maximize speed of I/O, and we really want to maximize speed of processing, and we want to maximize network. So in general, it's best to find instance types in your favorite cloud provider that satisfy those criteria: high network, high CPU, and high local storage. So in the case of AWS, it's the I series instances, and in the case of Azure, it's the LS series instances that have that kind of rich on-disk storage. Now, you may see people that advise, using just bog standard compute class instances and attaching them to your cloud provider's block disk storage. We find that this is suboptimal for two reasons. First of all, the latency is not quite as good because you are fundamentally, every time you're trying to commit data onto the disk, it's going out to some other machine and committing to the disk there, rather than committing to the local disk that's attached to that machine. Secondly, you are paying a whole bunch of extra money because when you're saving data to that disk, to that remote attached disk, you're actually saving it to multiple remote attached disks because your cloud provider is offering a durability guarantee that is durable against loss of a single machine. But if you are already using replication inside of your Kafka instances, you're replicating to 2 or 3 different brokers for every topic partition pair. That means you don't need to also pay to have the disk stored extra durable. You're already assuming I could lose a broker at any time. So why pay extra for that disk? And then finally, what about the case that you cannot read fast enough from your Kafka brokers? Well, in that case, you may want to run more distinct consumers or run more brokers so that the network pairing between two individual machines does not get quite as constrained. This is common in the case of cloud providers where they have this kind of shared fabric between their machines, and the more distinct routing paths you can provide them, the higher the bandwidth in aggregate you'll see across your cluster, even if it comes at the cost of having to run more replicas. So in many cases, we've chosen to run exactly one consumer for every partition, rather than using consumer groups and having a many-to-many relationship between partitions and their consumers. Another interesting thing is that a standard practice you'll see recommended over and over and over again is to use rolling restarts, right? Like we really like to do this idea of, I'm just going to slowly deploy to 1% and 2% and 5%, right? I'm just going to gradually roll it out. The problem with this in the case of Kafka consumer groups is that every time you add or remove nodes from that consumer group, for instance, if you're doing a version replacement, it has to rebalance which consumer is reading which partition. So you can make zero progress if you are replacing clients one by one by one by one by one that are trying to read off of your Kafka partitions. So in this case, it's a lot better to use a blue-green deployment or just, right, or otherwise just to literally turn 100% of it off and turn 100% of it back on, because you'll recover really, really quickly, as opposed to having this continuous dance of reshuffling partitions and never really getting started before you have to hand that partition off to someone else. And last and finally, it's really important to actually checkpoint your offsets on a regular basis, because otherwise, if you're only checkpointing every minute or two, you're going to lose 2 minutes of work in the event that you're restarted. So what are some ways that we can make this process faster to have higher throughput streaming clusters? Well, one thing is maybe you are not necessarily going to be the best possible expert on Kafka or your streaming technology of choice. So Confluent Cloud is out there, Google Cloud PubSub, Azure Event Hub, right? Like there are a myriad of solutions that are designed specifically for this event streaming use case. The trade-off is, while they do have access to way more machines than you will, they are run by someone else, and if it is not acceptable to pass the buck and say my cloud provider or Confluent is responsible for this outage, it means that you really need to have ownership of it yourself. The other facet here that you might consider is Apache Kafka is very fiddly to run. It might make sense for you to use a derivative technology like Red Panda, which implements the Kafka protocol, but itself is written in Rust rather than written in Java. So it's a little bit more modern, but we chose not to adopt it because we really wanted to have the flexibility to change providers and kind of to interoperate brokers. You can run a Red Panda cluster with a bunch of Kafka clients, producers, and consumers, but you cannot mix a Red Panda broker with a regular Kafka broker. Whereas what we wound up choosing to do was we wound up using Confluent's proprietary Kafka brokers, which actually work fine when run alongside vanilla Kafka brokers. So you can seamlessly migrate onto Confluent Kafka and migrate off of Confluent Kafka without recreating your entire cluster. I mentioned network bandwidth is really, really key, right? Like fundamentally, you might be limited by the throughput of your network interfaces. So one thing that you can do if you have more CPU available than your network is available is to use compression and to use really, really good compression. So if you use Z standard, it will give you something like 20% more bandwidth throughput than you might otherwise have if you are still using the previous default of snappy compression. And if you're not using any compression, sorry, that's really not a good idea. As I mentioned, replication can be really helpful, right? Like if you've already replicated the data for durability's sake to make sure you've got multiple copies of your data in different availability zones, you may as well read from that follower directly that's located in that same availability zone, rather than always crossing AZ boundaries to read from the current leader of the topic in partition. So using the local instance storage as opposed to paying for the remote attached disks is useful to do. And yeah, unfortunately, Honeycomb uses AWS, and in this case, unfortunately, Azure is in the situation where they don't charge you for transfer across availability zones because they want you to implement good data redundancy practices. Unfortunately, it costs us a lot of money to maintain that 3 availability zone configuration. And finally, why do you necessarily need to keep 100% of the data on that local SSD? Right? I mentioned earlier that in our case, the reason why we go to read from Kafka broker is because we're restoring from the checkpoint, right? Like we're restoring a Kafka consumer state from at most an hour ago or 2 hours ago. But we actually do want to keep something like 2 days of data around just in case we have a data eating bug. But if we're never going to actually read that, or at least not very commonly, we don't need to keep it on local fast SSD. We can go ahead and tier it to object storage in S3. So the other optimization that we found ourselves doing a lot is juggling instance types. So I mentioned the I-class instances are really, really good. So I-class instances are really, really good on AWS because of that property of that local attached storage. But at the time we were curious, why is that the case? Can we revisit that assumption and try using traditional compute attached to block storage? So here's the problem that we ran into, right? Like our size of data was increasing month after month after month. We were running more and more and more Kafka brokers, and we were spending more and more time hand-holding things if one of the Kafka brokers died. So we decided that we were going to try running using conventional instances and using attached block storage. The problem that happened was that it worked fine for about 12 hours. And then suddenly everything cratered. All of our metrics cratered, and it said that your throughput has gone to basically 0. We were staring at that and we were like, how is this possible? What's happening? And it turns out that Amazon and Azure and other cloud providers, every time you see something that says up to 25 gigabits per second, that means they'll let you run at 25 gigabits per second for 12 hours. And then they'll throttle you down to 0. This is not good behavior if you're trying to run a stable service, because it turns out that you can put yourself into a metastable state where your services wind up being able to run at the full capacity, but then as soon as you get throttled back, you're no longer able to run, or even in a state where it will run fine at steady state, but as soon as you lose a single node, you're going to be in deep, deep trouble. So after burning out a couple of Kafka brokers this way and almost burning out our team, we said, okay, no, we're going to go back to a stable configuration. We're not going to try this mixture of using compute and remote block storage. This doesn't make sense. So we eventually were able to migrate our data onto a newer instance family and also run many, many fewer of them, right? Like we went from running 30-something workers to running 6 workers because we eventually were able to get that balance of keeping the data we needed on disk and tiering the data that we didn't off to block storage. So you have to really, really be careful when you're playing around with hardware, not just to say, I'm going to trust the benchmark, or I'm just going to, if it runs for 2 hours, that's fine. You really need to actually check, does this run at steady state for long periods of time, and what happens if I lose a node? Am I still going to be okay if I lose a node? It's also crucial to identify performance bottlenecks by using the best possible tools, in this case, using performance profiling. By sampling and asking Java every 10 milliseconds, what are you doing, what are you doing, what are you doing, you can get a profile that tells you, this is where I'm spending all of the CPU time on the server. So if you start discovering CPU as a bottleneck, you might say, okay, why is it spending all of that time MD5 hashing this? It turns out that when you upload a file to Amazon S3, by default, the client for that is going to take a hash with MD5. I know it's not secure, but the point is to make sure that it didn't get corrupted by accident. But it'll hash it with MD5 before uploading it and give the checksum there too. So either by cutting out that MD5 step or by using a faster library, you can make sure that your Kafka broker is getting optimal performance. I think at one point we were spending 10% of our time computing MD5 really, really slowly. It was bad. So the other thing here that I mentioned is, can you survive losing a broker? A lot of people are like, oh, I just hope that'll never happen, right? Hope is not a strategy. So we go ahead and we actually kill our brokers regularly. We kill our consumers regularly. Our theory here is we'd rather find out about a problem or regression while it is still early enough to fix it, right? If you discover that you have, it takes you 12 hours to recover from losing a broker, and then suddenly it goes to 24 hours, that's a sign that you need to work on your broker recovery time or add more slack to the system. But if you weren't regularly testing that and suddenly you discover that you're going to be in a degraded state for a week if you suddenly lose a broker and you weren't planning for it, then suddenly that becomes an all hands on deck fire drill because another node might fail within the same week and then you'll be in serious trouble. So we actually discovered this 2 weeks ago. We discovered that our Kafka cluster was undersized and we needed to size it up because it was not possible to recover it during peak hours on a weekday, and it took through into a weekend for it to recover. Had that happened on Monday morning, we would have been in a very bad state. So by regularly testing the process of, I'm just going to terminate a Kafka broker, that enabled us to really, really kind of become confident in our data recovery strategy and confident that even if something did go wrong, our team had the capacity and knowledge to figure out how to restore things to working. So speaking of knowing whether things are working, how do we actually look at our streaming systems and figure out, is everything normal? So observability basically boils down to emitting the right data so that you can figure out what's going on. And we wind up eating our own dog food, so we have Honeycomb observing Honeycomb. And at the application level, what we care about is, for a throughput-oriented system, it's probably not possible to create a trace span for every event flowing through. If you have a smaller amount of data and you're tracking massive fan-out, it makes total sense to use a trace for every event that passes through your system. But if we're processing millions of events per second, not realistic to create another million trace spans per second, because then suddenly the size of our dog food cluster becomes 5 times the size of our production cluster. So instead, we wind up essentially aggregating that data and saying, every minute, give me a snapshot of what's going on. Tell me roughly what happened, and that's usually good enough. At the system level, we do track basic metrics. In the past, I know that I and others have kind of, been like, oh, metrics. But the reality is that metrics have a job to do, and that job is giving us kind of low granularity detail about what's going on in machines, not necessarily the best tool for what's going on user by user. You don't want a metric time series for every distinct user that you have, but for each distinct host, it's completely reasonable. And we like to track metrics on anything that might precede a cascading failure. For instance, if you run out of disk on your Kafka broker, that will cause the Kafka broker to completely choke because it prioritizes durability over availability. So if its disk fills, it's going to refuse to do anything, and it will refuse to do that until you give it enough disk. So we would prefer to make sure that we never dip below 20% disk, because heaven forbid that something prevent us from uploading and tiering that data to S3. Now it has to live on disk longer, and now that gives us a very finite runway of we must fix this problem within 3 hours or else, right? So we need to make sure we have enough headroom to preserve that property even if the tiering and being able to delete the data fails. So this means that we wind up tracking, how much bandwidth are we actually able to get produced, how much bandwidth are we able to get consumed, how well balanced is it between each consumer and between each broker. Where are we spending our time in aggregate on a function level for each consumer? So not request by request, but instead across all of the requests that I ingested over the past minute, where did I spend my time processing them? And then we track data like, what's the overall CPU, what's the overall amount of time spent garbage collecting, and so on and so forth. And this actually, so I mentioned that we started having some problems 2 weeks ago, so I want to show you what that actually looked like, because I think it's really, really interesting to see this phenomenon of we had some not so great balancing of our Kafka brokers. We were kind of in an imbalanced state, and then suddenly our financial services clients started experiencing much higher than normal traffic because people were suddenly concerned about an economic recession. And we wound up having to adjust on the fly the number of Kafka brokers and the balancing of our Kafka topics. So previously you can see that we are topping at something like 500,000 messages per second per Kafka broker on the week of April 1st. And we knew that if we had another week like that, where traffic spiked by a further 10 or 20%, it might cause a failure, either due to not enough CPU or too much disk consumption. So we threw more resources at the cluster and better balanced it because we realized that, if we didn't get ahead of this, that we were going to be in a lot of operational pain. And we track service level objectives not on individual CPU, because the CPU is not the reason why we're here. The processing of user events is. So we track SLOs based off of whether or not we're able to write successfully and not have to drop the data, whether we're able to respond to our clients promptly and say, yes, I got your data. And we track, between the time that you send an event into Honeycomb and how long, and when it's ingested and ready to query, how long does it take? Does it take, less than a minute, or is it taking in the 3 minutes, which is getting a little bit long, because you really like for if something happened to be able to see it right away. So what do we want to do next on our ingest side? So we had to roll out from having one set of Kafka clusters to 2 sets of Kafka clusters because we had to roll out, for European compliance reasons, a version of Honeycomb in Europe. And that doubled the number of clusters that we were running. And we didn't want the amount of work associated with our clusters to double at the same time that we doubled the number of clusters. So that meant that we had to add more automation. But the good news is that those clusters have been relatively problem-free because of the fact that when you start anything brand new, the utilization is going to be horrible. It's going to be like 5 or 10% utilized, and over time it'll actually reach a steady state, but until that point you largely don't have to worry about it, aside from automation to deal with updates and such. So having gone from 1 to 2, maybe we'll go from 2 to 3 this year or next year. That would be nice. Another challenge here is, as I mentioned, updates. So Kafka 4.0 just released. We expect Confluent will release a version of it. Their numbers are offset by 4 for some reason. But we are, I think, 2 or 3 minor releases behind. And we tend to only run kind of roll updates throughout our entire cluster about once every year, just because it's a lot of toil, it's a lot of work. And if something's working fine and we're in the support window, we don't necessarily see a reason to update. But at some point, we are going to need to kill off Zookeeper and migrate to the new Kafka self-consistency strategy using Raft. And as I was showing you earlier, right, we're in a state where our clusters had an imbalance of 2x or 3x between the least saturated and most saturated broker. We were able to kind of kick things by adding new brokers to the cluster and having the balancer rebalance things again. But we sometimes find that things get stuck in a state where there's that persistent imbalance of workload and we're not really fully utilizing the cluster, and we have to do some manual work to fix that. So Kafka is the beating heart of Honeycomb, but we'd rather that it produced less toil for us. And notably, Kubernetes does not solve this. The reason why we might want to move to Kubernetes for our Kafka cluster is just because it's the only service that's running on raw VMs for us at this point. So that's the reason why we want to move that to Kubernetes, and not for any of the kind of load balancing or update reasons. But we're hitting that point of having 15 Kafka brokers, and the last time that I kind of waved the white flag and said we're in trouble, we're running too many of these hosts, it's causing too much manual pain, was when we were running 30 of them. So we would like to think about how do we start scaling this cluster vertically rather than horizontally again. So that's the first half, talking about the query path, talking about the ingest path. Now let's talk about the storage and query path. So Honeycomb aims to be really, really fast, and therefore we've had to do some things that other systems might not have chosen to do as a trade-off. So we think that queries should return in about a second. If it returns in 100 milliseconds, that's great. If it's 10 seconds, that's marginal. And if it's 100 seconds, you may as well be using some other tool. That's not us. So fundamentally, people care, not just that we say, yes, we got it to the millions of events per second, but we actually have to give them charts and graphs and insights into what's going on. So I mentioned earlier that strategy of having things charted by Kafka partitions. So we have about 120 distinct Kafka partitions. each one of which is served by one or more indexing workers behind the scenes. But just because we've sharded it 120 ways does not necessarily in and of itself make it super fast. The reason? Because of fan-out. Every single time that you add a new parallel worker that you need to respond to something, you're adding a new failure mode, right? If you're querying 100 different things, you're going to hit the 99th percentile latency of your system every single time if all 100 workers must return in time for that request. So at some point, we had to think about how do we actually improve the speed beyond just scaling it out horizontally. So there are a couple of approaches here, one of which is to scan the minimal amount of data that you have to. So this is a common approach that is used all across our industry in terms of columnar storage, whether you're using ClickHouse or Parquet files or anything like that. The core idea is you want to segment your data both by time and by data type. So there's no sense in keeping all of the data on all of the names of your trace spans and keeping all of the data on the user IDs in the same file. Because what if you only want to query by trace span name and you don't need the user ID data at the same time? So by only reading the minimum set of columns, that dramatically cuts the amount of data that each individual worker node needs to sift through. And we can also segment by timestamp. We don't have to scan all 2 months of data every time someone asks about the most recent 10 minutes. We can just give them the most recent 10 minutes of data. But that does require us to keep kind of a metadata index of which timestamps are associated with which files on disk. We can do that. And fundamentally, then that also lets you implement expiry and say, you know what, the older data either needs to be thrown out entirely or it needs to be tiered off to longer-term storage. So by doing this aggregation of fields across time and subset, we're able to get reasonably good performance. The problem is you have more and more and more data coming in, and there comes to be a limit to the amount that you can scale up horizontally for that reason of tail latency that I mentioned, and vertically in terms of the size of the raw instances. So eventually, we got to a point in 2019 where we were actually having to throw out data from some of our customers that was mere hours old as opposed to days or weeks. So similar to what we chose to do with Kafka, we said, you know what, that older data, it's accessed less often. Let's just put it onto S3 or other object storage, and then if we need it, we can recall it back. So it does let us keep data for a fixed time range, but there's a problem. Now you still have the same pool of CPUs that are running your worker nodes, but you have hundreds of times more data. It's just living off in someone else's block storage. So you can grab the data back from S3 at need, but the problem is it gets slow. And specifically, it gets to the point of you have linear or worse than linear scaling, and you're sitting there waiting and waiting and waiting and waiting, and you're no longer just taking a sip of your drink, you're actually going and making a new cup of coffee. So fundamentally, this is an issue of capacity planning, right? Much like my dog really likes to play with her toys, except for then she gets bored and she wanders off, and then suddenly you have dog toys lying all over your floor, right? So it turns out that your neighborhood cloud provider has plenty of CPU available that they're happy to loan you at reasonably cheap rates, because unlike you, where you maybe are running 50 machines or 100 machines, your cloud provider might have tens of thousands or hundreds of thousands of machines just lying around. So what if we could tap into that and utilize that? So this is where the power of serverless comes in, because your compute provider will lease you machines by the millisecond and give you access to their full fleet and not just the ones that you've reserved on a long-term basis. So this graph shows us scaling out. We started at 10,000 parallel workers, and now we're allowed to use up to 70 or 80,000 concurrent workers, which I think is really, really amazing, because I would never, ever be able to afford 70 or 80,000 VMs to run flat out, right? Like I would just never be able to do that. But Amazon's willing to loan me those machines and charge me only for the milliseconds that I use. So that's how we're able to take this problem of having the storage grow out of proportion to the amount of compute available, to where compute is now our bottleneck, is now less of a bottleneck because we're only limited by the size of the total Amazon worker fleet and not the size of the number of instances that we personally have reserved. So now there's kind of this other aggregation layer it is true, right? Like, so we do have to fan out to any node that might have some data locally. And also those workers have to then fan out to serverless functions. So it starts looking a little bit like the Google Map reduced paper and so forth. And that enables the amount of time that it takes to scan to go up sublinearly. In fact, it's a nice logarithmic curve with the amount of data that you're scanning. So again, similar to what I said about, don't run it yourself if you don't have to. For smaller use cases, ClickHouse works fine. ClickHouse does scale horizontally up to the hundreds of nodes. But ClickHouse does not give you a scale of thousands or tens of thousands of nodes in the same cluster. It just doesn't. For larger workloads, Apache Spark, EMR, HD Insight, those technologies do exist. But those things are optimized for BI queries where someone is comfortable setting it running and waiting 30 minutes or an hour to get the results back. So the reason why we chose to implement all of this ourselves is because we had way more data than ClickHouse could handle on its own. And unlike the technologies of Spark and EMR, we really needed people to get access to the data in seconds and not minutes. So we get perfect utilization, which I think is really, really cool, right? Like, yes, it costs 3 to 4 times as much per CPU millisecond, but we only get charged for what we use. We don't get charged for capacity that we have reserved. Our cold starts are relatively cheap. They're only about 50 milliseconds, and 90% of our queries return within 2.5 seconds, which is more than adequate to meet kind of that 10-second maximum target. But you'll notice I put that little asterisk there. So Lambda is on-demand compute, but they didn't necessarily build it for this. They built it for the case of, I've got a website that I want to not have any servers running for. They don't necessarily expect you to turn up and suddenly demand 70,000 workers and then go away. And I imagine that Azure Functions has that same property of primarily being designed for the low-code use case rather than for the batch processing use case. But they do have massive pools powering it, and they're happy for you to send them money. You just have to talk to them. So the asterisk, because I'm an SRE. So Lambda does scale up, but if you ask it for more capacity than it has running worker nodes, it might tell you, go away, come back later, I need to scale out. And annoyingly, often it only will scale you up if you've been using the capacity consistently for a long period of time, in the tens of seconds or minutes. But what happens if, right, like we don't need a user to be sitting there waiting 10 or 20 seconds before Amazon gives us enough capacity. So we've wound up finding that they're reasonably flexible as long as you tell them in advance kind of roughly how much capacity you're going to use and what usage pattern you're going to have. So this is really interesting because we can see here the idea that effectively we're executing waves of traffic. There's your pointer, there we go. So you can see that we have roughly during this time window in which we had some users actively querying us, we had about 40,000 workers that were warm, spun up, waiting to serve traffic. And as soon as there came in a wave of requests, we started processing them about 40,000 requests at a time. And then the next 40,000, the next 40,000 or so until we'd finished the entire batch. And yes, we did have to cold start, it looks like maybe 10,000 new workers, but not that many new workers were needed to spin up to service that request. So we can actually kind of see this pattern of what does Lambda actually do when you have a spiky workload? How long does it keep those workers alive until it scales them back in? So retrying is obviously a thing to do when you get a not enough capacity, although you should follow your cloud provider's recommendations about backing off and so forth, and making sure that people are aware of what you're intending to do. So yeah, cold starts are this interesting challenge, but the main thing you can do to alleviate the cold start time is to make your software package smaller. So instead of shipping the entire set of things that's capable of talking to Kafka, the set of things that's capable of merging the results together, all we care about is processing individual packed files on S3. So we have had to implement a separate main function, right? A separate main function, a separately compiled binary that's only about, I think, 20 or 30 megabytes in size, in order to make sure that our cold start time is fast, rather than having our cloud provider sit around forever waiting to spin up new workers for us. So yes, 90% of traffic does come back within 2.5 seconds, but it turns out that the other 10% can be considerably slower than 2.5 seconds. In fact, something like 0.5% of our requests never come back. It'll just hit the 60-second execution timeout and it'll say no results. So our trick there is impatience. We'll just automatically retry the slowest 1% of requests. And it turns out that those succeed fine because it's not a fixed property of this individual file is slow. It's just there's a natural latency distribution, and if you retry the slow requests, then you'll get back the request fast enough that you'll have 100% of the data covered and be able to return to the client. Sometimes we have to either send giant payloads to our workers, or we'll have to receive giant payloads from our workers. I mentioned the case of needing to run analysis across gigantic traces. What happens if someone asks to query a trace that has 1 million spans in it? That return value will be pretty big. That return value might even be in the tens or hundreds of megabytes. So it turns out you can use object storage as kind of temporary swap space rather than consuming memory to transmit all of the data in one go. And then finally, the cost. Yes, it is possible to have a foot gun with Lambda or with Azure Functions. You can do that via a circular loop where you're just recursing and invoking and invoking and invoking, or you can actually have that from a well-coded use case where the computer is doing exactly what you told it to. It's just scanning a lot more data than you thought. So I just had to set up various alarms and capacity constraints to say, you know what, if any one customer starts consuming more than $300 a day worth of serverless functions, we want to understand what's happening just so that we can figure out, is there something to optimize? Is this working as intended? Is that customer making us enough money that it will, that it will pay for the utilization? But we can make it cost less by using the most up-to-date compute technology. So in the case of AWS, you can execute against Graviton. I don't know whether Azure lets you execute Azure functions against Cobalt, but by using the latest versions of CPUs, by using the latest compute architectures, it winds up costing the cloud provider less power and less licensing fees to Intel. And that means that you can get better cost price performance. So by moving to Graviton, we were able to reduce our Lambda bill by about 20 to 30%, which was pretty cool. So overall, my recommendation to you is it's possible to use streaming data. It's possible to use serverless functions to do big data workloads, even if it's not necessarily what it's labeled for on the tin. You just have to be thoughtful about what's your use case, what's the problem you're trying to solve, and not just, I heard this awesome talk from Liz and I want to try this today. But think about what's the business problem that you're solving. So fundamentally, anything where the state can be decentralized and moved off of individual compute workers into generic object storage is a good use case. And something where there's the capacity to shard the data into at least thousands or tens of thousands of parallel work units. It doesn't make sense to stand up serverless functions just for the sake of processing a mere hundreds of work units. You kind of need thousands or tens of thousands to get that economy of scale. And you need something that is amenable to processing each shard independently. You cannot have cross chatter between different shards. If there is that, you need to think about data locality. For instance, that thing that I mentioned earlier about making sure that all the data associated with a single trace is stored in a single file, rather than having it spread across multiple files and multiple partitions. Now, your reduction functionality can be the only place where the data comes together, rather than needing each mapper to do the work and talk to the other mappers. But be aware that if something is not having a human impatiently waiting for the result, right? If you are running a business analytics workload where it's okay for it to come back in 30 minutes or an hour, there's no point running those serverless functions flat out for 3 hours, right? And paying 3 to 4 times as much. So it's really only effective if you're actually trying to brute force something that is a reasonably sized workload that's big enough where it makes sense to pay the cost of calling out to a serverless function as opposed to looking at it locally, but not where it's so big that you may as well actually spin up a dedicated set of machines for it. And we did find some problems when we were initially migrating over software architectures. We found that we actually were experiencing slower performance for a while when we were using Graviton because some of the libraries we were using were did not yet have assembly in ARM. So tuning the batch sizes is really important. Doing some profiling, checking out, hey, is this still spending time in the places that I expect it to? If it's not, is there anything that I can do to make it go faster? Making sure that you're tracking how many cold starts are you incurring, how long is it taking per cold start, what's the size of your binaries, how much concurrency am I actually getting from my cloud provider versus how much have they advertised to us, and making sure you have the appropriate guardrails around cost. So overall, streaming and serverless can be really, really powerful because streaming lets you ingest the data at large scale and to persist it safely. And then the serverless technology lets you inspect it at your own whim whenever you need to without paying for the cost of storing that data and keeping all of that crunching capacity available 24/7. So that's what I have for you today. Thank you very much. Please enjoy a picture of my puppy, who is a golden retriever mix, and thus is aptly named because our storage engine is called Retriever. All right, I've got 5 minutes for questions if there are any questions. I also do have stickers if you're interested either in Honeycomb or Kubernetes stickers. Yes?
If you shard by trace, what if you wanted to query for just everything that happens just by time?
Yes, the question was if you shard by trace, what happens if you want to query for everything that happened by time? So we are making sure that each trace winds up consistently in the same shard, but there's not one shard for every single trace. Right, so each shard will have one or multiple, usually like multiple in the thousands of distinct traces inside of each segment. We call our shards. So each segment will have a variety of different traces that were all ingested around the same time. And those traces have trace spans that said, oh, I started at 5:05 p.m. or I started at 5:06, 17 seconds or whatever. So for each segment, we track when the oldest and newest trace span within that segment, when that trace span actually says on its timestamp, not necessarily when we received it. So if you send us data to backfill from 2 months ago, we'll record that trace started 2 months ago and ran from 2 months to 2 months and to 1 month and 29 days and 23 hours ago, right? And that way we know which segments we should be querying based off of what time range you asked for. Does that make sense?
Yeah, so, and then you merge them together?
Exactly. So then we merge the results together from multiple segments. Yeah, exactly. Right. Like, so we're kind of processing all of the segments that might overlap with the time range we're interested in and matching all of the traces within those segments. And then afterwards, we're combining that data together to give you kind of an individual trace waterfall or a time series saying how many of this trace span there were or so forth. Yeah.
So with the compression, how do you train the dictionary?
Yes, so we found that for the compression of the data, for the Kafka brokers, the CPU is relatively cheap because it's essentially thrown in alongside the on-disk storage. So we're able to use Z standard and just brute force it. We don't apply any kind of special custom compression to the data flowing in and out of Kafka. For the case of the serverless workers, it's very, very different because the serverless workers are, right, like the CPU time is very precious and dear to us because we pay dearly for it. So we've actually found that using less good compression that is cheaper on the CPU works out to be better than trying to maximize compression ratio, right? Like object storage is cheap, and up to a point you have relatively unlimited network capacity coming in and out of the serverless function. So we actually use LZ4 compression. Like we're not using Z standard, we're not using like any of the super sophisticated compression algorithms because speed is the most important thing, even at the cost of things being 30%, 40% larger object size. We do build custom dictionaries, and yeah, the way that we do that is we just look at what data values are we recording. For instance, if you have a field that's called HTTP status code, I can guarantee you it probably has 200, 403, 404, 500, right? Like, so yes, we'll track kind of those frequently seen values and construct a custom dictionary on that. And then after that, that then encodes things as, okay, this is a 200 instead of encoding as a 200, I'm just going to mark it as value 0, right? Like it's the most common value we see. So that kind of compression we do, but at a certain point you have to just let LZ4 do its work. We've tried some experiments with, so one of the most impactful things we did, users don't actually tend to care how many microseconds, how many microseconds after the milliseconds and seconds and hours and minutes something is. So we found that just trimming off the microseconds field reduces a lot of the entropy. The other things that we do after that are things like delta encoding and so forth for integral values, where we find that compresses a lot better than keeping the full set of entropy associated with the numerical values.
Is that in the column storage?
Yeah, exactly. So that's the columnar storage layer. Again, these are things that largely, if you're using ClickHouse will do that for you. The piece that ClickHouse does not do for you is that kind of fan out to doing many query workers. They're actually surprisingly close to being able to do it. I hope someone will do it at some point, because you can run a separate ingester ClickHouse cluster and then have a separate query ClickHouse cluster against the same data store. But we just, at the time, ClickHouse was not mature enough for our needs, and we felt that we would have better control of our own destiny by implementing our own columnar storage engine. But we're happy to share everything that we know because of, we value a robust ecosystem, we value, talking about how we can make the process of working with telemetry easier for everyone.